Hey, Keeney coming to you with another video for the nerds. So this is going to continue on with our Autel Ultra series. This one is sort of going to be a subcategory in that series. This is going to be the first of a few videos specifically talking about the oscilloscope function or the oscilloscope app in the MaxiSYS platform. So I don't know if all of the scopes are the exact same across all of the Autel products. I'm guessing they're all pretty similar, but in any case, this one will give you an intro and some details behind the oscilloscope usage. And I will probably break these videos down. This first one will be introductory overview. This is where stuff is. The second, third, maybe fourth video will be specific usages with inside the scope, because there are some details that I want to get into on the different features, and there's no way that that would do all in one video well. These are all probably going to be long enough, just like all the others. So if you want to learn more about that scope function in this tool line, hang on or hang out for a while, and we'll see where this goes. To kick this thing off, I want to go over just a couple of specs and a couple of the hardware layout design stuff also, because I think it's relevant depending on what you need to do and or what you want to do in the type of testing that you're going to be using these tools for. So to start, the scope specs are depend on, as far as sample rate goes, depends on how many channels you're running. According to the user manual, if you're using channels A and B only, or just like 1 to 2 channels, you can get up to 8 million samples per second. If you start adding 3 to 4 channels on your scope, you're going to be limited to about 20 million samples per second. As far as the scope goes, I'm going to spin this camera around in a minute. The hardware of the VCMI, where the leads plug in to the actual hardware, is the type of setup that I do personally prefer. Not all scopes are this way. Specifically, I'm pretty sure the snap-ons are not. But with each scope, with each set of scope leads that you have, there's obviously a power side and a ground side. Where that ground side of the scope lead goes to, so 2 leads of the scope, where this actually goes to on the hardware circuit board of the scope interface device, the VCMI in this case. In this scope, these grounds are isolated. So if I have 4 channels plugged in, if I do resistance checks from each one of those 4 channels on the ground path of the scope, each of the scope negative or ground leads is isolated from the other 3 negative or ground side leads, and I'll demonstrate that in a second. So that's a feature to me that is pretty important to have, especially when I'm trying to do voltage drops across either really power and or ground circuits. This comes in really handy, whereas you can still do that type of testing for sure with the snap-ons where they all have a shared ground. So when you plug 4 channels into the snap-on scopes that I have used, there's continuity between all of the grounds. Now we can piggyback grounds to the same place, but we can choose to do that with the Autel scope. With the snap-ons, as soon as one channel is grounded, all 4 channels are grounded for the ones that I have used to this point. And like I said, it not that you cannot do voltage drop testing across like multiple drops across the same wire or the same circuit with snap-on. You can. You typically will just have to take multiple measurements and then add them, subtract them, whatever. Whereas with this one, I can do them all at the same time, get them on the same screen at the same time. So with that, I'm gonna spin this around. I can show you what kind of little setup we've got going on my box. So we've got just normal multimeter, snap-on meter from forever ago, the Ultra, the VCMI scope. And so we've got 2 meter leads coming out of the DVOM, and then on the Autel side, we've got coming out of the back. So the DVOM leads actually plug into the rear of the VCMI, and those are just going to run there for our testing. I also have channel A hooked up to the scope leads, so that just runs to these two. So we're going to be doing a few different tests here. I'm going to try and get this camera set up so we can see most of all what we're doing. We're definitely going to have some glares on those screens. It's the best I can do, so it is what it is. This was a bit difficult to try and get everything on the same screen at the same time, but we'll give it our best and just keep moving forward. Over here on the left, we've got actual DVOM leads. Coming out here in the middle, we have the Autel DVOM leads. And on the right-hand side, these are our scope leads. And I want to do a couple demonstrations on the continuity of the boards for each of these. So, for example, we're gonna just connect in some normal leads. So DVOM leads. We've got resistance and we've got the beeper on, super annoying, but we can at least, hopefully you can hear that to see what's going on. So what I want to show first is the resistance of the scope hardware itself, because different multimeters, different scopes have different impedance. And if you are testing sensitive circuits, that impedance matters because it will have a greater effect on weaker circuits. So there are some vehicles, I forget your make model, but a Chrysler or Jeep comes to mind, where they run bias voltage on some of their powertrain circuits that you wouldn't normally expect to have bias voltage on. So like, I think fuel pump relay for some reason comes to mind on the power side. So they're actually looking, I could be wrong, but to best of my memory, there's a vehicle that had actually a weak 5 volts on the power side of the fuel pump relay. And when you use a DVOM or a scope, depending on the impedance, you would actually be able to see that 5 volts as a bias voltage, or it would pull it down to like 3 volts because the impedance in the measurement device you were using is lower. So if we have something, I think the standard's about 1 million ohms, and if you have like a 1 million ohm meter, it would pull that down to like, I think 3 volts or something. But if you had like a 10 million ohm, or you had something to rig up where you gave the multimeter or voltmeter, whatever you're using, more impedance, or a device with higher impedance, it would keep it at closer to 5 volts. It'd come up to like 4.8 or 4.7 or something. So the whole point of motorcycles riding by, so the whole point of doing this test is so you can understand the impedance differences on the measurement tools. So we are measuring our measurement tools so that you can have an idea of what type of impact you will see when testing on sensitive circuits on cars. Because when you're pulling or looking at specific voltages on a given circuit and you see a weird number like 3 volts or 3.7 volts, That's not a normal voltage we typically see in cars, and we need to understand that that might be there because the car has a bias voltage, but our measurement tool is actually impacting that circuit. So to demo this, be aware, this is where some of the details matter, again for the nerds. When we switch this device from on to off, or use different settings or connect it to the tool, the impedance changes. This is really trippy, especially if you're leaving your scope hooked up to the vehicle and taking other measurements. So if I'm using both of these at the same time on a car, for whatever reason, typically because for whatever reason, if I turn that or the battery dies on the VCMI, or I lose Wi-Fi connection between the tablet and the VCMI, the resistance, the impedance of that hardware changes. And if you don't know this, it can throw you for a loop. So right now we have nothing open on the scope. So it says no recent items when I open all the tabs up. On the actual device, we have none of the lights on, so this is off. But we have our DVOM set up to ohms. So I'm going to connect, if I can do this on camera. So I'm going to take snap-on DVOM negative to Autel I'm already on the wrong circuit, look at me. To Autel DVOM negative. I'm going to take snap-on positive to Autel DVOM positive. And we can see we are at very, very high impedance. So we have, I forget what this reads up to, but it shows open, which is fine. So we're still connected. I'll leave that in screen. What I'm going to do now is I'm going to turn on the VCMI. I should get some lights going and whatnot. But I want you to watch, while that's powering up, I want you to watch our DVOM at the same time. Perhaps I'll cut this if it gets to be too long. So we actually had no pun intended, we had a fluke with our snap-on meter. For some reason it locked up on me. So we're backing up. We have snap-on DVOM connected to Autel DVOM like we did, and the VCMI is off, powered off. Before it read open, that was wrong. Something went on here. Now you can see we're reading 25 million ohms. Now I'll come back over, turn on our VCMI. As that powers up, we'll see if anything changes here, and then also we'll get our app up and running. At this point, we now have the VCMI powered on. It is connected Wi-Fi to the tablet. Now let's do this again and open up our multimeter. And now we can see this changed. It went open as the VCMI actually switched circuits internally. Now our resistance for that Autel DVOM dropped to almost 11 million ohms. So right off the bat, we're above 1 million ohms, which is probably good for most testing scenarios for your equipment. But we do want to know that that's still a pretty big shift when we actually get this thing powered up and turned on. Likewise, I'm going to measure the resistance of this tool now. So if I go from DC voltage to resistance, now both of these are set to resistance. That's why everything says OL. But I'm going to come over here and switch this to our millivolt scale. And there, boom. So the Autel, we can already see some differences here too. The Autel puts out about 200 millivolts to do its circuit testing, and I forget already what it was, but I think it was 100 something millivolts that the Snap-on puts out to do a resistance check. But now we can see and compare the two together. So about 10 million ohms, 10 to 11, they are more closely aligned in this scenario. And if I go to the normal voltage scale, it becomes interesting. I don't actually know what this resistance is on the actual voltage scale because it appears to be, let me change, even if we change the scale here, it won't matter. We'll hit 10 mega ohms. It still shows open. So that tells me that whatever impedance this has on the normal voltage scale is probably higher than this can read. So that's higher than our 10 million ohms or whatever. It is, I've done this a couple times before shooting this video to make sure I was getting the correct readings, and this same thing happens every time. The reason I think that's important too, this is we're gonna flip you around for this one. So let's adjust, shall we? One thing I did forget to mention in the beginning of this video, where we were talking about some specs and things that I think are important, it is very important to know that, in my experience with my tool, the Autel scope does glitch out more times than I would like to say is okay. And what I mean by glitching out, if you watch I think it's like the world's most expensive tire pressure gauge video I did, where we're doing pressure transducer testing, feeding that into the scope. Towards the end of that video, there was an offset by whatever PSI on the sensor. Whenever I was using the sensor, the offset of reading atmospheric pressure from the beginning to the video to the end of the video was different. That was a glitch in the scope itself, and it happens, and it's burned me twice on a vehicle because I was looking for a specific signal change, and it kept showing the old signal live across the screen. Like watching data traces, it actually cached the trace in the software, and it was playing back the previous capture. And no, I didn't just record it and play it back, because when I disconnect my leads in these two scenarios, when I disconnect the leads from the car, voltage drops to 0. When I reconnected the leads to the car looking for a change in the previous pattern, the old pattern showed back up. Rebooted the scope, rebooted the tablet, same thing, and now my voltages or my traces updated like I expected them to. So it's really important to understand that this tool does, by design or not, I have no idea, but this tool does cache data and can sometimes glitch out and play back the wrong data. How I have overcome this, because I'm a scope whore and I use this thing all the time, even for stuff that's not needed for, the way that I have overcome this robustly is every time I walk away from the vehicle for more than 5 minutes, I power down the VCMI. And unless I have some crazy template saved on the scope, I also close the scope app on the MaxiSYS tool. When I do both of those, every time I come back, I'm golden, and I don't have any of these cached image problems. So I do that regularly. And if I'm every time I use a scope, I'm always doing something in depth, maybe more than necessary. But every single time I come back to that same thing to do multiple versions or iterations of my next test, when I do this process of shutting down the VCMI and rebooting the oscilloscope app, I do not have that problem. Certainly we could have the conversation of, is that acceptable or not? That's not really a conversation I care to have right now, but what I will just communicate to you is that, hey, be aware that it happens, and if you can deal with that, I recommend turning it off and back on pretty regularly in the middle of your test, especially if it's an important test or a test that is time sensitive or temperature sensitive, or you can, or intermittence. That's where it gets you. That's where it really frustrates you, is when you have an intermittent issue, and it happened to me, and the vehicle behaved away. I didn't see it in the data, and I didn't know until lots of testing later that the data I was looking at was cache data, and that's frustrating. So just be aware of that, and here's a mitigation for you moving forward if you run into that issue. Back to this. So the reason I did several of these tests before shooting this video is I wanted to make sure that we're not having any type of cached image stored with our snap-on DVOM being on the high voltage scale and the Autel DVOM resistance reading open. So this is normal, this is repeatable, and this is what I expect to see on this test. So I don't know what the impedance of this meter is on the normal voltage scale. I don't have another DVOM laying around the shop. I've got a couple others elsewhere. So if I do some sort of, post-edit test, maybe I'll add that in or do a separate video. But short version, I don't know what the impedance is on this scale. When we switch it to our millivolt scale, we're at about our 10 mega ohms. So there's that. Now let's do the same type of test, but I'm going to do this with the scope instead of, I'm going to clear all those, instead of the DVOM. So I'm going to power down the VCMI. I'm going to disconnect my snap-on DVOM from the Autel DVOM, and we should be done with these leads for now. We're going to bring in the scope leads. I'm also going to connect a couple of my actual leads to this. And here's the first thing that I want to show you. Switching to resistance, turning our buzzer on so we get buzzing and stuff when we make connections. Here's what I was talking about with the snap-on versus the snap-ons that I've used versus the Autel. So the outside case, I don't know how great you can see this. I'm just roll with me. See if I can. Whoops. No, we're just gonna make a mess out of everything. Okay. So these outside cases are ground. So this black wire connects to the outside of these scope leads connections, and the positive, the red, goes to the inside of this. So what you will see is we've got our resistance or connection there. If I touch channel A ground to channel B ground, I have no change. There's no continuity between the ground circuits in any of these channels. So I'm touching channel A and channel C, channel A, channel D. There's no continuity between these. If you do this with the snap-on leads that I've done, there is continuity. So I'm touching the case and the case. Obviously we have connection there, but nothing between the two. This is important to know if you are doing certain type of voltage drop testing. You need to know what your equipment is set up to do and how it functions. That said, now let's get rid of these leads. I'm now going to connect the channel A scope. Our VCMI is off, and we're going to connect snap-on multimeter DVOM to Autel oscilloscope on both of these. and see what our resistance is. So right now it says that it's open. I'm inclined to agree with it, but we're going to turn this off and back on just to be on the safe side. See, we had a glitch there. I don't know what's going on with this and why it's glitching like that. I don't know if there's some circuit that's being powered up by this whenever we do changes like this. I'm not sure what's going on, but when we cycle it, it seems to come back to life. And we got about the same reading. So here's where we are. VCMI off. We've got 6 million ohms in your scope leads. I'm going to power on the VCMI. As that powers up, we'll do this just like we did before for the DVOM side. We're going to see if that changes. If it doesn't, then I'll probably cycle it again. But we may cut this until it comes back on. At this point, we have we turned on the VCMI. It's Wi-Fi connected to the tablet. So I'm going to go ahead and run to our oscilloscope function. And boom, we've already got changes. We have 2 million, oh, there it goes. So you can see that we had a 2 million ohm increase. Now we've dropped down to 1 million ohms. This is interesting to me because, again, on the super sensitive circuits on a vehicle, if you can have a fluctuation in a bias voltage between 1 to 6, 7, 8 million ohms, if it changes that voltage and you don't realize that that's happening, we want to have this in the back of our mind. I probably said that absolutely terribly, but I think you get my point. Depending on what we're doing here, we can have an impact change. I do not remember if we changed the voltage scales. By the way, this is another spec that I think I already forgot to talk about in the beginning of the video. The maximum input voltage before damage occurs to the scope is 200 volts. So you don't have to remember it, but just remember we've got, if you just do a normal pull-up, the highest one is 200. According to the user manual, 200 volts is the max. So if you have a circuit, a collapsing magnetic field circuit that is going to spike over 200 volts, that's when you're going to need your attenuator. So keep that in mind, 200 volts max. In any case, change it from 200 volts, it didn't change anything. You go to auto, and when I say anything, I'm looking at the impedance differences. There's no difference there. We'll go to 50 millivolts, no difference there. But I want to show this too. I'm trying to remember how I got to it. So right now we're connected via Wi-Fi. Let's do this first. Let's close the oscilloscope. Boom. Changes. So now we're back to our 6 million ohms that we saw before. But we're still connected via Wi-Fi. If I disconnect, I don't know if that will change. So it appears not to. But when we do have the Wi-Fi connection and these circuits become activated, we do get that resistance change from 6 to a brief, 7 or 8, and then drop down to 1. So just interested in how this stuff works. Again, video for the nerds, but just knowing your equipment, measure your measurement tools. I think it's an important thing to do, and hopefully this will provide some insights on how these actually function together. I had a change of mind. Originally, I had planned to go through the oscilloscope app and do an overview of all the functions and whatnot in there. I had intended for the hardware analysis section that we just went over to take a lot less time than I think it did. I've cut this video a few times and I think I've talked way more than I intended to. So we're going to push off an actual introductory to the application itself to the next video. and we'll record that here, hopefully in the near future is my plan. But this one is going to stick to the hardware analysis and the different impedances and connectivities of each of the circuit boards for the tool that you're using. So that's all I got for you today. I will catch y'all in the next one.